Hello friends, welcome to Susan and John MathTube. So we continue revision with past papers, and I made this video specially to discuss chi-square goodness of fit. So I'll repeat once more, chi-square goodness of fit, because I saw this particular question being asked once. Normally they used to ask chi-square test of independence again and again and again, but remember, in your syllabus there are three things. One is chi-square test of proportion, then chi-square goodness of fit, and chi-square test of independence. And I saw what you call goodness of fit being asked once, so let's learn this procedure. So I hope you're okay with chi-square test of independence or test of association of attributes. So here what they do is they want to check, this is a very useful method. Goodness of fit is like very useful. So I'll write the title once. Goodness of fit. Okay. So let me tell you when to use this. So look at this. In many cases, we believe that the experiments follow a certain pattern. Pattern in statistics is called distribution. For example, we believe that the traffic follows the accidents in the roads follow Poisson distribution, or maybe we believe that the length of vehicles follow normal distribution, or we believe that the amount of electricity used by a certain town follows gamma distribution. Now, in goodness of fit, what we do is we check whether our assumption is matching the reality. That is, we take experimental values and compare it with the predicted values. Predicted values means predicted by using the distributions. I hope you understood. Once more, let me try to make it very clear. Look at this. In the beginning of statistics, we learned that many things around our world follow patterns, and patterns made into statistical form using data will be called distributions or functions. Mathematically, we can call them functions. But now we are going to check how much a function is matching with the reality. Okay, this is one of the best questions, and this is the question they asked, I think last year or the year before. Okay, in an experiment on pea breeding, Mendel obtained the following frequency of seeds. So look at this. This is the experimental value, and this is the theoretical value. Look at this. This is what the theory suggests. Theory tells if there are 9 round and yellow, there should be 3 round and green, and there should be 3 wrinkled and yellow, and there should be 1 wrinkled and green. So theoretically, this is what we believe, and according to Mendel's experiment, this is what he observed. So remember, goodness of fit is the test that we are going to do here, and in every goodness of fit, just like our test of independence, just like our ANOVA, the null hypothesis and alternative hypothesis are fixed. Null hypothesis is like it follows the theoretical proportion. That means our observations and the theory match. And of course, the alternative will be it does not follow the theoretical pattern, the theoretical proportion. Okay. Now, as usual, the level of significance. Okay. I'm going to do with 5%. You can experiment with 10% level of significance. By the way, are you ready with your statistical table? I want you to take chi-square table and be ready with that. Okay. Now, next comes calculation. Calculation is very simple. As usual, observed, expected, observed minus expected the whole squared, divided by expected. I think I can manage it within a small table. Okay, so what are the observed values? There are 4 categories, right? 315, 108, 101, 32. And expected means what is the proportion? It should be 9 is to 3 is to 3 is to 1. So basically 9 out of how much? 9 plus 3, 12. 12 plus 3, 15. 15 plus 1, 16. So 9 by 16 into, what is the total here? Take a calculator and count. 315, 108 plus, okay, 315 plus 108 plus 101 plus 32, 556. So 9 by 16 out of 556 should is the expected value, and that is 312.75. And similarly 3 out of 16 multiplied by 556, so you get 104.25. Similarly 104.25. Last one, 1 out of 16, that will be 34.75. Now look at this. This is the observed, the reality, and this is our expectation because of the distribution or the proportion. Now what we do is we find the difference between observed and expected, just like we did in independence. So use a calculator. Be very careful. The denominator is separate. And I got the following values. You can confirm it. I got 0.0162. I did it a little bit fast, so please make sure you confirm the values. You should practice again and again and again so that you become confident for the exam. I'll repeat, watching this video will make you understand, or watching this video will help you a little bit. But if you want to score marks, then you should practice more questions. So look at this. What's the formula for chi-square calculated? I hope you remember O minus E the whole square by E. And anyway, I got the value 0.47 something. Okay, now step number 4. In step number 4, what we do is we calculate chi-square tabulated. And the chi-square format is degree of freedom and alpha value. And degree of freedom, look at this. Let's make it once more. Let's make it very clear. In independence testing, in independence of attributes or association of attribute testing, degree of freedom is row minus 1 times number of column minus 1. In proportion testing, it's simply n minus 1. Here also it is n minus 1, where n stands for the number of different categories. So here there are 4 categories, so the degree of freedom will be 3. And alpha, in the question they have given 10% also, 5% also. I will do one, I am leaving the other one for you. So alpha is 5%, that means 0.05. Now you can take the chi-square table and you can put it in degree 3. You can go down 1, 2, 3 and find 0.05, and the value will be 7.815. Now I want you to draw the chi-square distribution and mark the value 7.815, and on the tail you have to write reject, and on the other part you have to write accept. Okay, and now step number 5, decision. So come on, tell me, what's your decision? 0.47 is in the acceptance region. So our decision will be to accept H0. So basically it means the ratio is good. It is following the ratio when we take a 5% risk. So that's it. But I want you to do more problems. I have kept 2 problems here so that you become confident. And it will be better if you find more problems online or in any favorite statistics book that you have. So let's read this question. Over a long period of time, a research team monitored the number of car accidents, etc. Test the hypothesis whether these data are random sample from a uniform distribution. Now look at this. Uniform distribution means we are expecting the same number of accidents will happen every day. So basically these are the observed values. So if it is uniform distribution, then can you tell me what are the expected values? Okay, I'll tell you what to do. You count 60 plus 54 plus 48 plus 53 plus 53 plus 75 plus 77. That is 420 divided by 7. So we are expecting 60 accidents per day. Did you understand how I got that expected value? If it is uniform, then every day there should be the same number of accidents. So what I did is I took the total and I'm using 60, 60, 60, 60, 60 as the expected value. Try it, give it a try. And another question, in order to test whether a 6-sided die, by the way, they can ask like 4-sided, 10-sided, like you can Google about it. You might have seen only 6-sided die because it is more popular in the South Asian side. But there are like what you call 4-sided dice also, 10-sided dice also. You can Google the picture and Mr. XYZ throws the die again and again and collects the following information. Test whether it is biased or not. Now think about it. If a die is not biased, the probability of getting 1, 2, 3, 4, 5 and 6 will be 1 by 6, 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 1 by 6. That is what you believe. Now Mr. XYZ is like what you call very suspicious about the scenario. So he did that experiment and now he's asking whether the die is biased or not. Before playing Ludo and before playing snakes and ladders and gambling with dice, etc., you can actually do a real testing. You can use this, you can use goodness of it and check whether the die that you have is biased or not. But remember, the more number of, if you do this experiment like 1,000 times, 2,000 times, then you can actually know whether the die you have, the dice that you have is biased or not. Anyway, these are the observed values. This is the reality. Now, what is our expected value? 1 by 6, 1 by 6, 1 by 6, 1 by 6. So what I'm going to do is I'm going to do 117 plus 20 plus 29 plus 20 plus 18 plus 16 division 6. So I'm expecting 20, 20, 20, 20, 20, 20. Okay, that's it. It was a small video. Now I'll be back with another small video, that is gamma distribution. So keep on revising. So till then, bye.